Greetings, everybody. Learning is a hobby here. I want to post this video. Uh, Admittedly, a few days late. I wanted to post this on Sunday, but this semester's the winter semester has been a little bit more hectic than I had previously anticipated. So it took me a while to get the solutions to Chapter 5 in Spivak done. Actually, I'm not done with them yet, but I have enough for one video right now. There's still a few problems I want to do, so I'll actually probably make a part 2 to this video on some of the remaining problems from Chapter 5. But I have quite a number of them from the exercise set at the end of Chapter 5 to look at here today. So I want to continue with that. If you've forgotten what Chapter 5 is about, the video is posted already on the main channel. It was posted actually all the way in back in the summer. I just haven't gotten around to doing the exercise set for it, which I am at least 3/4 of the way done with now. So I'm going to go through the stuff that I've finished already. And like I said, I'll probably do one more video just to finish up a few of the other problems that I want to look at in that section. And then we'll continue with the next chapter, which is chapter 6. So let me bring up the solutions to the problems that I did. As usual, I tend to skip the more rote type problems just because I find them to be, I mean, they're important to do, but I find them to be a bit boring. So I tend to do the problems that I find interesting or that look interesting to me. So that's how I chose the problems here, like I usually do. So I start with question number 6. And again, this is from the exercise set for chapter 5 in Spivak. So let's actually read out the question here first. So question 6 says, suppose the functions f and g have the following properties for all epsilon greater than 0 and all x. If 0 is less than the absolute value x minus 2 less than sine squared epsilon squared over 9 plus epsilon, then absolute value f of x minus 2 is less than epsilon. And if 0 less than absolute value x minus 2 less than epsilon squared, then absolute value g of x minus 4 less than epsilon. For each epsilon greater than 0, find a delta greater than 0 such that for all x, and then there's 4 pieces to the problem. So here I just do them one at a time. All right, so they want you to find the for each epsilon greater than 0, they want you to find a delta greater than 0 that works. Okay, so here with with part 1 of question 6, if 0 less than absolute value x minus 2 less than delta, then absolute value f of x plus g of x minus 6 less than epsilon. So again, the goal here is to find a delta that works. So that's what I'm writing down here as the solution. So here, notice that absolute value f of x plus g of x minus 6 is equal to f of x minus 2 plus g of x minus 4, right? Because minus 6 is the same thing as minus 2 times minus 2 minus 4, right? And by the triangle inequality, that's the same, that's less than or equal to absolute value f of x minus 2 plus absolute value g of x minus 4. So what we want is absolute value of f of x minus 2 to be less than epsilon over 2. And same thing for absolute value g of x minus 4. We want that to be less than epsilon over 2, because then over here we could say this is less than epsilon over 2 plus epsilon over 2, which is less than epsilon or equal to epsilon. So just based on the information that they gave us here, so based on, for f of x minus 2, if you're in this neighborhood, then this is within epsilon, and same thing here, if you're in this neighborhood, then you're within epsilon of 4 for g of x. So just using that fact, if I choose delta 1 to be sine squared epsilon over 2 squared over 9 plus epsilon over 2, and if I choose delta 2 to be epsilon over 2 squared, then if we take delta to be the minimum of d1, if the minimum of delta 1, delta 2, then that'll work. This will be less than epsilon over 2. This will be less than epsilon over 2. So the whole thing will be less than epsilon. All right, so I'm just taking epsilon over 2 here and just plugging it in for epsilon, and that gives me what I want. Right? Again, like I said, that just comes from the properties that they gave us here. Okay, here's part 2. If 0 less than absolute x minus 2 less than delta, then absolute value f of x times g of x minus 8 is less than epsilon. So again, we want to find the delta that works. So here's my solution. So absolute value f of x times g of x minus 8 is equal to absolute value f of x times g of x minus 2g of x plus 2g of x. Over here, it's like I added 0, so it doesn't change the value of anything. Minus 8. And again, by some properties of absolute values and the triangle inequality, whoops, there should be, sorry, I just realized there's a typo here. There should be, where am I? Over here. There should be another vertical line here. So that's less than absolute value f of x minus 2 times absolute value g of x plus 2 times absolute value g of x minus 4. So, just using the triangle inequality and factoring some things. All right, we need this to be less than this by the lemmas that we looked at in the summary of the chapter. If this thing is less than this, then the product here will be less than epsilon. So we need this to be less than this, and we need this to be less than this in order for this to be less than epsilon. So we take delta 1 to be sine squared, minimum, this simplifies to epsilon over 10. Minimum epsilon over 10 comma 1, all squared divided by 9, plus minimum epsilon over 10 comma 1, and take delta 2, that's for so that gives us a bound for this, and then take delta 2 to be, if you simplify this thing up here, epsilon over 2 times 3, that gives you epsilon over 6. So we need delta 2 to be minimum epsilon over 6 squared, comma 1 squared, or in other words, minimum epsilon squared over 36 comma 1. Right, and then you choose delta to be the minimum of those two numbers, and that gives you what you need. That'll make this less than epsilon. All right, part 3. Again, these all refer back to those 3 lemmas that we looked at in the summary of the chapter. So if 0 less than absolute value x minus 2 less than delta, then absolute value 1 over g of x minus 1 over 4 is less than epsilon. So we need to find that delta. So again, you just using the lemmas that we had in the chapter, we need absolute value g of x minus 4 to be less than the minimum of 4 over 2 comma 16 epsilon over 2. If you simplify these, you get minimum 2 comma 8 epsilon. So going back up here, using this property, you just take the square of that and take that to be delta, and that gives you what you need in order to make this less than epsilon. Okay, question 4. Again, same idea. If 0 less than absolute value, x minus 2 less than delta, then we want f of x over g of x minus 1/2 to be less than epsilon. So again, we need to find this delta. So again, just using a similar trick that we did in part 2, I can rewrite this expression here as f of x over g of x minus f of x over 4 plus f of x over 4. These two sum to 0, so it's not, it doesn't change the value of anything. Okay, and 1/2 you can write as minus 2 over 4. That's the same thing, right, when you reduce. And then using the triangle inequality and factoring, we get that that's less than or equal to the absolute value of f of x times absolute value 1 over g of x minus 1 over 4 plus 1 over 4 times absolute value f of x minus 2. And again, just referring back to the lemmas from the chapter, we need, in order to make this happen, we need absolute value f of x minus 2 to be less than the minimum of 1, or epsilon over 2 times, in this case, y0 would be 1/4. So epsilon over 2 times 1, absolute value 1/4 plus 1, which simplifies to give you the minimum of 1 comma 2 epsilon over 5. So just plugging that in for epsilon here in delta 1, we get this. And then we also have to have a bound for absolute value 1 over g of x minus 1/4, right? Because that's this part here. Okay, and again, just appealing back to the lemmas from the chapter, that'll happen if we make this less than minimum 2 comma 8 times minimum 1 epsilon over 6. And here you can actually simplify this because 8 obviously is greater than 2. So if the minimum here is 1, you end up using 2 as as the minimum value. So actually here you can simplify this just to 8 epsilon over 6. So you take the minimum of 2 or 6 epsilon, sorry, 8 Wait, did I write this upside down? I did write this upside down, didn't I? Sorry, let me fix this. This should be 8 epsilon over 6, not the other way around. So actually, this should be 4 over 3. Sorry about that. Okay, so if you choose delta 2 to be minimum 2 epsilon, 3 epsilon over, sorry, 4 epsilon over 3, all squared. Again, by the properties in the instructions for this problem, then you take the minimum of delta 1, delta 2, and it works out. It'll give you what you want. All right, so that's question number 6. All right, going on to question 11. Let's read it out first. Suppose there's a delta greater than 0 such that f of x equals g of x when 0 is less than absolute x minus a, less than delta. They want us to prove that limit as x approaches a of f of x equals the limit as x approaches a of g of x. All right, so here's my proof. Let limit f of x as x approaches a equal some number m, and let limit g of x as x approaches a equals some number n. And what I want to show is that n is equal to m. Right, so choose delta prime such that delta prime is between 0 and delta, strictly between 0 and delta. Then that means that absolute value f of x minus m will be less than epsilon over 2, and g of x minus n will be less than epsilon over 2. Furthermore, f of x plus minus g of x will sum to 0 by over here. Right, if you're within this neighborhood, then these two things are equal. So then we consider absolute value n minus m. That's equal to 0 plus n minus m, right? If you add 0, it doesn't change anything. And I can write 0 as f of x minus g of x, again, by what I just stated over here. These two things are equal in this neighborhood. Okay, then that's, if I just rearrange things here, that's equal to f of x minus m plus n minus g of x. And by the triangle inequality, that's less than or equal to absolute value f of x minus m plus n minus g of x in absolute value. That's less than epsilon over 2 plus epsilon over 2. And when you add these together, you get epsilon. So that shows that these fixed constants are less than any positive epsilon, which means it has to be 0. Less than or equal, right? It has to be 0. Okay, going on to question 12. I think there's a bunch of parts to this one too, so let's just start with part A. Part 12A says, suppose f of x is less than or equal to g of x for all x, and they want us to prove that limit x goes to a of f of x is less than or equal to the limit x goes to a of g of x, provided that these limits exist. So here's my proof. So let f of x less than equal g of x for all x, then that means that that's equivalent to saying 0 is less than or equal to g of x minus f of x for all x. And here, if I take the limit of both sides here, I get 0 is equal to the limit as x goes to a of 0, which is equal to the limit as x goes to a of g of x minus f of x. And then I can use theorem 2 to distribute the limit over the difference here. That's equal to limit x goes to a of g of x minus limit x goes to a of f of x. So I get 0 is equal to this expression. Sorry, there should be inequalities here, shouldn't this? Sorry, I wrote this up kind of quickly. Sorry, this should be less than or equal. Less than or equal. Okay, so 0 less than or equal to this. You just add limit x goes to a of f of x to both sides, and that gives us what we want. Right, that's part A. Part B says, how can the hypothesis be weakened? We can weaken the statement in A by just, instead of letting it be true, letting f of x less than g of x, less than or equal to g of x, be true for all x, we can restrict it to some delta neighborhood around A. And that's because limits are a local property of functions. They're not global properties, they're local. So if this is true over some interval, then the limit will be of f will be less than or equal to the limit of g over that same interval. Okay, and then going on to part C. If f of x is strictly less than g of x for all x, does it follow that limit x goes to a of f of x is strictly less than limit x goes to a of g of x? And the answer is no. And here's an example that demonstrates that it's not necessarily true. So if you take f of x to be equal to the piecewise function 1 minus x squared, where x is not 0, and minus 1 if x equals 0. So it looks like if you drew this, it looks like the parabola. Let's see, actually it should be up here. It looks like this parabola, except at 0, it's defined to be minus 1 rather than equal to 1 here. Okay, ignore this circle here. And then define g of x to be equal to 1. That's the constant function that looks like this. Okay, then notice that f of x is strictly less than g of x for all x. However, if you take the limit of f of x as x goes to 0, the limit from the picture you can see is equal to 1. And actually, same thing for the limit of g of x as x approaches a. So here, this is not strictly less than. It's less than or equal, but not strictly less than. So this doesn't hold in general. Whoops. Okay, question number 13. Suppose f of x is less than or equal to g of x is less than or equal to h of x, and that limit as x approaches a of f of x equals limit as x approaches a of h of x. Prove that limit x goes to a of g of x exists, and that limit x goes to a of f of x is less than or equal to limit g of sorry, I'm getting tongue-tied here. Limit of g of x as x approaches a is less than or equal to limit h of x as x goes to a. This is called the squeeze theorem, if you remember from calculus 1 or whatever. This is the squeeze theorem. All right, so here's the proof. Let L be the limit of the function f and h as x goes to a. So because we're assuming that the limits are the same, then there exists delta 1, delta 2, such that absolute value f of x minus L is less than epsilon, and absolute value h of x minus L is less than epsilon when 0 is less than absolute x minus a less than delta, and 0 less than absolute value x minus a less than delta 2. These are delta 1 and delta 2, that respectively. Then choose delta to be the minimum of those two. Okay, then if 0 is less than absolute x minus a less than delta, then this is less than epsilon, this is less than epsilon, and that implies that L minus epsilon is less than f of x is less than L plus epsilon. Same thing for h of x. So we get this string of inequalities. So L minus epsilon less than f of x less than or equal to g of x less than or equal to h of x less than L plus epsilon. Okay, which means that g of x is between L minus epsilon and L plus epsilon from the above string of inequalities. And then I can subtract L from both sides. That gives me this inequality here, negative epsilon less than g of x minus L less than epsilon. But that's the same thing as absolute value g of x minus L less than epsilon. So that shows that not only that the limit of g is L, so it exists, it also shows that the limit of g of x as x approaches a is the same as the limit of the other two functions. So it's, in other words, it's equal to L. All right, going on to question 14. I think there's several parts to this one as well. Let's look at part A. Prove that if limit x goes to 0 of f of x over x equals L and b is not 0, then limit x goes to 0 f of b of x over x equals b times L. He gives us a hint here in the book, so I'll write the hint here as well. He says write f of b x over x as b times f of bx over bx. The b's canceled here, right? So that's the hint. And let's look at my proof. So here, assume that b is not 0. Then since limit x goes to 0 of f of x over x is equal to L, that means that there exists delta greater than 0 such that absolute value f of x over x minus L is less than epsilon over b when 0 is less than absolute value x less than delta for some positive delta. We can pick delta prime less than delta over absolute value of b. Okay, if we do that, then this expression here, right, absolute value bx will be greater than 0 and less than delta, which means that which means that x is, if I choose this, sorry, I wrote this backwards. 0 less than absolute value x less than delta prime implies this, right, because delta prime is less than this. So that implies that absolute value bx is less than delta and positive. All right, let 0 less than absolute value x less than delta prime, then that makes this thing. Before I use this fact, I can factor out a common factor of b from both of these, and then just factor out the absolute value by taking the absolute value. So actually, this is equal to absolute value b times absolute value f of bx over bx minus l. Right? If you factor b out of this, you just end up dividing by a factor of b. So we get this thing, and this, since we're in this neighborhood, is less than absolute value b. That's just this absolute value b times epsilon over absolute value b. And notice these cancel and you get epsilon. So that shows that the limit is bl, right? We took this minus bl here. So that shows that the limit is b times l. Okay, in part B, he asks what happens if b is 0. If b is 0, we get a constant on top here. So limit x goes to 0, f of 0 times x over x is the same thing as the limit x goes to 0 of f of 0 over x. This limit doesn't exist because the expression here blows up to infinity on one side and negative infinity on the other side, depending on what the sign of f of 0 is, unless f of 0 is 0, then the limit will be 0. But if not, then this limit doesn't exist. All right, part C. Part A allows us to find limit x goes to 0 of sine of 2x over x in terms of limit x goes to 0 of sine x over x. And he asks us to find this limit another way. So I just used a trig identity to do it. There's other ways you can do it. So here, if you take the limit as x goes to 0 of sine 2x over x, remember from trigonometry, sine 2x is the same thing as 2 cosine x sine x. So I'm just replacing sine 2x with that expression there. So these two limits are equal. And then I'm just distributing the limit here using theorem 2. That's equal to the limit as x goes to 0 of 2 cosine x times limit x goes to 0 of sine x over x. The limit of 2 cosine x as x goes to 0 is 2, and the limit of sine x over x is 1, so you get a limit of 2. And the fact, here I'm just telling you what I'm using by theorem 2, and the fact that this trig identity is true, and the fact that limit as x goes to 0 of sine x over x is 1. Okay, going on to question 18. Prove that if limit x goes to a of f of x equals L, then there's a number delta greater than 0 and a number m such that absolute value f of x less than m if 0 less than absolute x minus a less than delta. Okay, so here's my proof. So assume that the limit of f of x as x goes to a is L. That implies that there's a delta greater than 0 such that absolute value f of x minus L is less than, for example, 1 when 0 less than absolute x minus a less than delta for some delta greater than 0. Then for any x, 0 less than absolute value x minus a less than delta is implies that f of x is between L minus 1 and L plus 1. Therefore, we can choose any m such that m is greater than or equal to the maximum of absolute value, the maximum of absolute value L minus 1 or L plus 1. So it follows from that. Right, question 19 asks us to prove that if f of x is this function here, it's defined to be 0 if x is irrational, and it's defined to be 1 if x is rational. Okay, then they want us to show that limit x goes to a of f of x does not exist for any a in R. So here's the proof. Assume for the sake of contradiction that there exists two real numbers, a and L, such that limit x goes to a of f of x equals L. Then for example, for epsilon equals a quarter, there should exist a delta greater than 0, such that for 0 less than absolute value x minus a less than delta, absolute value f of x minus L is less than 1/4. And to derive our contradictions, we do this by cases. So for case 1, let's assume that L is greater than or equal to 1/2. Okay, then choose a rational number in the interval between a minus delta and a plus delta. I should say here, this, I'll just say sneaks in density of R minus Q and Q in R. We haven't, or he hasn't talked about the density of the rationals in the reals or the irrationals in the reals. I believe he does that later on in the book, or at least hopefully he does. But this proof does sneak that concept in here. So technically we're kind of, there's a bit of hand waving here. Like, how do we know that we can do that? But I don't know another way of doing this. So this is the way that I'm doing it. So assume that L is greater than or equal to 1/2. Choose a rational number in the interval from a minus delta to a plus delta. Then that means absolute value of f of x sub r minus L is equal to 0 minus L, right? Because f at an irrational, sorry, x at a rational number is defined to be 0. That's equal to L, and L we said was greater than or equal to 1/2. Notice that that is greater than 1/4. So this is a contradiction. It contradicts that we should be able to make this less than epsilon, the epsilon that we chose, which was 1/4. All right, so case one is a contradiction. Let's move on to case 2. So here, assume that L is less than 1/2 and choose an irrational number in the interval from a minus delta to a plus delta minus q. Then absolute value f of xi minus L is equal to absolute value 1 minus L, because when you evaluate f at an irrational number, it's equal to 1 by the definition of f. And here, since L is less than 1/2, 1 minus L is greater than or equal to 1/2, which is greater than 1/4. And again, that's a contradiction. Okay, so since case 1 and case 2 exhaust all possible values of L, that means that the limit does not exist for any real number A. Okay, 2 more problems that I have done so far. This is question 20. Which is similar to the one that we just did. Prove that if f of x equals this piecewise function, it's defined to be x if x is rational, and it's defined to be negative x if x is irrational. Then limit x goes to a of f of x does not exist if a is not 0. Okay, so here's my proof. Assume for the sake of contradiction that there exists a, L in R, where a is not 0, such that limit x goes to a, f of x equals L. Then there exists delta greater than 0, such that for epsilon equal to absolute value of a, absolute value f of x minus L should be able to be made less than absolute value of a when x is less than absolute x minus a less than delta, right? That's what it means for the limit to exist. We proceed by cases, just like I did in the last one. So case 1, assume L is greater than or equal to 0, then choose an irrational number in the interval a plus delta over 2, comma a plus delta minus the rationals. So this is an irrational number, in other words. Then absolute value f of xi minus L is equal to negative xi minus L by the definition of the function f, the way that we defined f. And that's equal to xi plus L. Because of the absolute value, right, you can factor out the negative, and the absolute value of -1 is +1, and xi is positive, and so is L. Or 0, L could be 0 too. And xi is a number that's greater than absolute value of a, because we chose xi to be in this interval here. So we get something that is greater than absolute value a plus L, and this is greater than or equal to absolute value a, which was the epsilon that we chose, so that's a contradiction. Okay, case 2, assume L is less than 0 now. Choose a rational number in the interval from a plus delta over 2 to a plus delta intersect q. So in other words, this is a rational number. Then absolute value f of xr minus L is equal to absolute value xr minus L by the way we defined f, the function f, right? When you evaluate f at a rational number, it's just equal to the input value. So xr minus L. And then here, again, xr is positive because it's in this interval here. Xr minus L equals xr plus absolute value of L. That's because the value of L is negative, so this is actually a positive number. So you can actually just take this, this is equal to this, in other words. Notice that, again, this is greater than absolute value A plus absolute value L, which is, this should be greater than or equal to. That's greater than or equal to absolute value A. So that means that this is greater than the epsilon that we chose. And again, this is a contradiction. Therefore, Since case 1 and case 2 exhaust all possible values for L, that means that the limit doesn't exist for any A not 0. Yeah, I think if I remember correctly, I think we proved that the limit as A approaches 0 does exist, and I think it's equal to 0. I think we did that in the chapter 5 itself, but this shows for all other values of A, the limit doesn't exist. All right, this is the last question that I think this is the last question that I did. Like I said, though, I'm gonna do a few more problems in chapter 5 exercises, and I'll post that in part 2 to this video when I get around to doing them. And hopefully I'll be able to post the solutions to the chapter summary for chapter 6. Hopefully I'll be able to do that this week. But anyway, let's finish up exercise 21. There's two parts to exercise 21. There's part A and part B, but part B implies part A, so I'm just going to do part B because this is the more general statement. So here part B says if limit x goes to 0 of g of x equals 0, and absolute value h of x is less than or equal to m for all x, then limit x goes to 0, g of x times h of x is 0. So here's my proof. Okay, so assume the hypothesis, let limit x go to 0, g of x equals 0, and assume that h of x is less than or equal to m for all x, for some m in r minus 0, the real number is minus 0. If m is equal to 0, it follows directly, right? If down here, if you look, if m is 0, then this product is identically 0. So when you take the limit of a constant, it's just a constant. So it works in that case. So really all the meat is in looking at these cases where you don't worry about m being 0. Okay, then absolute value g of x less than epsilon over m whenever 0 less than absolute x less than delta for some delta greater than 0, because the limit of g of x is 0 as x goes to 0. Then for any 0 less than absolute value x less than delta, the absolute value of g of x times h of x is equal to absolute value g of x times absolute value h of x. That's just by properties of absolute value. And that g of x is less than epsilon over m because we're in this interval here. And h of x is always less than m, so this will be less than epsilon. And that shows that the limit of the product is equal to 0. Right, and that, like I said, that's the last problem that I had time to finish up in chapter 5. So let me stop the screen share. Okay, so like I said, there's still a few problems coming up from this chapter that I want to post. I just haven't had time to get around to them yet. But hopefully within the next few days, I should be able to post part 2 to this video, and then I'll move on to the chapter summary for chapter 6. All right, guys, I'll see you in the next video. Keep learning, and again, let me know what you think in the comments. If you wouldn't mind, press that subscribe button. It helps the channel out. And actually, I forgot to mention this. I should have made a video about it, but maybe I'll try to do something special for it at some point in the near future. But the channel finally reached over 1,000 subscribers, so thank you guys so much for helping me out and for enjoying the content. I hope that you get something as much joy out of the channel as I do, and information, and I hope you learned stuff when you watch the videos. But if you do enjoy the content and you haven't subscribed, please do me a favor and just hit that subscribe button. It doesn't cost you anything, and it helps me out a lot. Also, just to promote, I have the Patreon page, which you should check out and see if you're interested in that. That's $5 a month, and you get a lot of extra content for that. All right, so I'll see you guys in the next video. Until that time, keep learning, everybody.